So today we will be discussing the 2020 Physics A-level paper. Under that essay paper, I'll be considering the part B of question number 10, and so we'll begin with this question, which comes under the lesson matter and radiation. First, let's read the question and understand what are the concepts behind this, and then we'll move on to the questions systematically and answer the answer using the methods that they need us to answer ASF in the marking scheme itself. So a monochromator is an optical instrument that can be used to produce a monochromatic beam of photons. So since this is a discussion, I'll explain briefly the concepts regarding the passage that which you are given here. So what do you mean by a monochromator? So actually it's a optical instrument that has the ability to produce photon beams which are monochromatic. That means the beam is like same in all the correction of the rays are the same, in the sense it's a monochromatic beam of photons, that means light particles, in a photoelectric experiment. So this is used mainly in conducting experiments regarding to identify the photoelectric effect of Einstein, and in a photoelectric experiment, a monochromatic beam of photons produced by a monochromator. So this monochromator produces monochromatic beams in order to conduct the experiment in relation to photoelectric effect. I hope you understand the reason behind this situation or the experiment. And it passes through a rectangular apparature perpendicularly incident on a metal plate kept in a vacuum chamber as shown in the figure. So for you to understand, let's first see what this monochromator looks like. So it turns out to be it turns out to be something like this. So this is the light source, and you have placed a concave mirror for the reflection of light, and then the concave mirror to focus the beam of light, and then there is array detector, and then these signals are passed on to a computer, and the visual detection observations of the experiment can be concluded. So the monochromatic beams are these, and this setup is overall is a monochromator, and this helps in identifying various experimentations conducted within the photoelectric effect. So let's further not go in depth with this mechanism, but we'll directly move on to what the questions are. So initially the monochromator produces a beam of photons of wavelength 100 nanometers. So 100 nanometers. Photons of the wavelength 100 nanometers. So take HC product as 1240 electron volt nanometer for all the relevant calculations. H is the Planck constant, C is the speed of light. Now we'll start on with the questions and we'll go directly into the answer, and the way the marks allocated is highly important here, but I'll be writing only the necessary steps where then you could identify that this method of answering is what you should do in your exams as well. So name the wavelength region of the electromagnetic spectrum where 100 nanometer of radiation belongs to. So in this question, you must be able to revise get the estimation of the wavelengths for radiations of electromagnetic spectrum. Here we first see according to the that chart, there's a chart that you should be able to revise, but I won't be taking the image of that chart in this occasion, but I'll simply depict it from the side where there is higher frequency and low wavelength. And somewhere here the frequency gradually decreases and wavelength gradually increases from here to here. So first comes gamma rays, then X-rays, then ultraviolet rays, then visible, then IR or infrared rays, then TV waves, then comes the radio waves finally. So this you should be able to remember, not the values actually. So according to that, 100 nanometers come under UV rays. So the answer comes, name the wavelength region. So UV region. Answer 1. Then number 2, calculate the corresponding energy of the 100 nanometer photons in electron volt. So we know that if the Planck constant is H, energy of waves with frequency F, we know the relationship E equals HF. According to that, we also know the very famous equation which comes under waves and oscillations, V equals lambda F, and so we can subject F as here V is velocity is the velocity of light, so C divided by lambda. So here I'll take E equals HC divided by lambda. Afterwards, because lambda is actually 100 nanometers as given, okay, 100 nanometers. So we'll better substitute HC product also available. So we have both the HC product and also the lambda. So I can write 2000 to 1240 divided by, no need to apply units in actually physics except for the last answer, but in chemistry please keep in mind to apply units in each and every position, so it's not relevant here. So next divide this by 100 nanometers. Since nanometers is the common, this nanometer cancel off. For you to identify that, no need to convert nanometers to 10 to the power minus 9. In the sense here nanometers will cancel off. So the answer they ask is in EV product. So the answer is 12.4 EV. Question number 3. Considering the wave particle duality, calculate the momentum of the photon with the above energy. So value of H is given. photons can act as a wave or even as a particle. You know that. So this is called the wave particle duality of photons. This is exceptional in the form of light. So according to the wave particle duality of photons, we can find the de Broglie wavelength. You might have known relationship that in chemistry in your first lesson, atomic structure. It's quite famous in the de Broglie wavelength, lambda equals h divided by mv, something like that. Hope you guys could remember it. So de Broglie wavelength lambda is equal to the Planck constant divided by the momentum, or else you can write this as h divided by p. P is simply the momentum. Thereby, what they are asking is directly calculate the momentum. So to find the momentum, you need to subject this p. Subject this p and then you get h divided by lambda. You get the momentum. So p here, h value given 6.6, 10 to the power minus 34 joules second. Then divided by lambda. What is lambda? We know 100 nanometers. There, keep in mind to convert the nanometers into to the 10 to the power minus 9. 100 into 10 to the power minus 9 meters. So the momentum equals 6.6 here. 10 to the power 2 cancels off and it becomes 10 to the power minus 7. When it goes to up, it becomes 10 to the power minus 27. The units of momentum you better directly apply it, kg ms minus 1. That's enough. So that's the answer for the third part. And now we'll see part B. Part B. Here also I'd better. We did this and this. Now part B. Derive an expression for intensity I. Also, the energy flowing through unit area per unit time of a monochromatic parallel beam of n number of photons, each having energy E and passing through an area A during a time t. So just what do you mean by this whole thing? They are asking some kind of an expression related to intensity. So considering the intensity, you know, you don't need to revise you should not be a parrot here, kind of a parrot, like remembering what is there any formula for intensity? No need like that. Just they've given the definition in the brackets also, energy flowing through a unit area per unit time. Unit, that means some kind of something like that. I just imagine, okay, energy flowing through a unit area per unit time, something like this. Okay, let's think, because they have already given it in the definition. Just think, you know nothing about intensity, you have no idea what this intensity is, and you need to derive an expression. So the definition is already given here. So just imagine what kind of an answer might be suitable in this occasion. So now just consider, I'll write in statements. Okay, just let's begin with writing statements. Number photons through unit area during time t. Okay, number photons per unit area in unit time. It will be something like n divided by a t. So energy of a photon, energy, the symbols that we should be using also, note them down separately. We need to get the symbol n, then we need to apply a, then we need to apply T, then we need to apply E, and that's pretty much all, right? Yeah, we need to use all these symbols, and you know there's no n here, so just type is like this. Anyhow, there should be n here, right? Because there's n number. No? So let's see about that. Just forget this and just look into this matter. So energy per photon, that means for one photon is E. So the total energy passing through, total energy passing through unit area per unit time, what could it be? So that is called the total intensity. So no, just write this down. N divided by AT into that energy. Okay. So next, the intensity. What is the intensity? That is I equals the same expression, A divided by A, N divided by AT into E. So finally, I equals NE divided by AT is our final answer. If you just write this expression, you'll be able to acquire most of the marks, because they ask us to derive. So you need to define each and every term and the way you are going to apply, and then finally how you would be able to conclude that this intensity came because of this. Due to this reason, we managed to collect these terms, compound separately, and then finalize this answer, finalize this expression. So yeah, that's how. So we are done with the first one in part B. Second one, if the intensity of 100 nanometer monochromatic beam of photons shown in the figure above is 9.92 10 to the power minus 8 Wm minus 2, that is the units of intensity. So, and the area of the rectangular aperture is 3 millimeters into 4 millimeter area. So how many photons pass through the aperture per unit time? So 1 EV equals to that amount. So what are they asking? So I think they are asking how many photons passes through the aperture per unit. So it seems to be a kind of substitution for the expression we obtained above. So just manage with substitution parts in this format itself. So again, write down the equation for the betterment, and then intensity is given, right? Intensity is given. That is 9.92 into 10 to the power minus 8. So yeah, so N is, we don't know. Energy we obtained above, right? We have the energy which we got before, that is 12.4 EV. 12.4 EV, and area we have we need to convert this to meters, that is 3 into 10 to the power minus 3 into 4 into 10 to the power minus 3 into T. T in the sense per unit time is 1. So here EV product, they have given the value for EV, right? So we better remove this EV and substitute 1.6 into 10 to the power minus 19 joules. Minus 19 joules. And now substitute the subject in here. Once you subject in, we have 9.92 into 10 to the power minus 8, then into 12 into 10 to the power minus 6, then divide by 12.4 into 1.6 into 10 to the power minus 19. Then the value of n you'd be getting, we can simplify this now. The denominator, numerator comes as 119.04 into 10 to the power minus 14. The denominator, once simplified, you get 19.84 into 10 to the power minus 19. And finally the n value, number of photons passing through the aperture per unit time. Unit time I just inserted 1, actually no need of that either. Thereby the n value comes 6 into 10 to the power 5, right? And afterwards the final answer n is equal to 6 into 10 to the power 5 amount of photons passing. So number 2 is also done. So part 3, so we didn't complete it yet. If the metal plate shown in is a silver plate of area 2 mm into 2 mm, calculate the number of emitted photoelectrons in unit time from the plate, assuming each incident photon emits one photoelectron. So they have given a specific area now. So we know that the number of for the third one, number of electrons passing is 6 into 10 to the power 5. So they have given us a new area, that is 2 into 10 to the power minus 3 into 2 into 10 to the power minus 3. And we had the area which was given before. Out of that whole area, they have mentioned a certain specific region, not the total area, but the area less than that, a certain part, we should be out of that whole part. Okay, the whole area we took before is 12 into 10 to the power minus 6. That was this particular part, right? This was the area you see here. So that is this 12 into 10 to the power minus 6. 12 into 10 to the power minus 6. Okay, so 6 into 10 to the power 5 into 4 into 10 to the power minus 6 into 12 into 10 to the power minus 6. So finally the number of electrons passing through that 2 to 2 millimeter area, 2 millimeter into 2 millimeter silver plate area of that metal plate, then is 2 into 10 to the power 5 number of they are mentioned as to find the photon, since one photon emits one photoelectron, n photons release 2 into 10 to the power 5 number of photoelectrons. Here just photons. One photon in the sense is one photoelectron as mentioned in the passage. So that question is also done. So part C, question number 1. The work function of the silver plate used in this experiment is 4 electron volt. Find the minimum and the maximum values of kinetic energy of the metal kinetic energy of the emitted photoelectrons in eV. The work function given, then we need to find the minimum and maximum values of the kinetic energies in electron volts. Okay, so relationship for that, because we calculated in the second part of the energy of 100 nanometer photons is 12.4 electron volts, right? We got at the very beginning. Okay, hope you remember that. An electron can be absorbed whole 12.4 electron volts and comes to the surface, and but so that the electron cannot move from the surface, but the electron absorbs only a work function energy of 4 electron volts as if asked in the question. As given in the question, it's 4 electron volt is the work function. That means 4 eV is released. So out of the whole amount 12.4 eV, we need to remove 4.0 eV. That is 8.4 eV, right? That 8.4 eV is the energy stored in the electron as kinetic energy. Stored kinetic energy of the electron. Out of the whole electron volt, 4 acts as the work function, and this is the energy, kinetic energy remaining. It is something like this. You will later be reminded or learn afterwards. So before, you might have known this also. I'm not going to highlight this concept here, but it's just keep in mind that this is a specific equation. You can easily do the calculations using the concepts in this part. So E equals HF plus psi. That is, this is the energy, this is the HF product or the kinetic energy released, and this is the work function. So kinetic energy, this acts as actually this acts as the kinetic energy. This was the 12.4. This is what we need to find out, and this work function was already given. So this EK value is 8.4 eV. That's how I got it. Okay, this is just a separate method. And find the minimum and maximum values of kinetic energies. So once you come to the point, the maximum kinetic energy should be this, right? Since this is the kinetic energy as of in the equation. So the rest is the work function out of the whole thing. So maximum, finalize the answer by writing maximum kinetic energy is 8.4 electron volt, and the minimum kinetic energy is just 0. Yes, 0. Okay. Afterwards, that part is also finalized. Number 2, the the monochromator is adjusted to produce monochromatic beams of photons of wavelengths from 100 nanometers to 500 nanometers in 50 nanometer increments, and for each wavelength, maximum kinetic energy Emax of photoelectrons emitted from the silver plate is measured. The variations of Emax with the wavelengths of the photon beam is shown in the figure. What are the values corresponding to A and B? So they are asking about A and B as of in the graph. Number 2. So according to this graph, y-axis is the maximum kinetic energy, x-axis is the wavelength. So we should be able to create a graph because the Emax, the equation I have written before is this equation I am going to repeat, HF plus psi, no? So they are considering the Emax here. If you consider the Emax, this equation changes its format to E equals, equals HC divided by lambda, no? So because Emax, this becomes HC divided by lambda naught because it's a maximum energy, right? Lambda naught, and thereby this is kinetic energy Ek max and the psi. So we can what they are asking, there is the A and B kinetic energy, maximum kinetic energy equals Hc divided by lambda naught minus the psi. And because the maximum kinetic energy, there is actually maximum kinetic energy is here, that is actually 0, right? So since Ke max is equal to 0, we need to write 0 equals Hc divided by lambda naught minus psi, and thereby psi equals Hc divided by lambda naught. And so next we need to find the lambda, the A and B. A gives the lambda and B gives the Emax. So we defined the Emax already, and now what we need is to find this lambda naught. So to subject lambda naught, we have Hc divided by psi. So Hc product we were given in the question itself as 1240 eVnm, and divided by psi value was also given in a previous part as 4 eV. This eV to this eV cancels off, and lambda naught is 310 nanometers. So that's all about A and B. This is kind of A and that is kind of B. Part 2 also concluded. Now 3. Same experiment is repeated for a gold plate with the work function of 5 electron volt. Copy the graph in figure 2 in your answer sheet and draw clearly the corresponding curve for the gold plate in the same graph. So in this case, just substitute this K. Now the third part we have Ek max, Hf minus psi, and then Ek max Hc divided by lambda naught minus psi, and this becomes a 0, and then Hc divided by lambda naught minus psi. Then again subject the lambda naught as we did before, Hc divided by psi, then 1240 eVnm, and they told that the gold plate, this is for the gold plate, no? For the gold plate the work function is 5 electron volt to electron volt cancels off, and then this lambda naught for the particular gold plate is 248 nanometers. Beforehand it was 310 for the other plate. I can't remember the plate there, silver plate, right? For the silver plate. So let's draw a graph. for the gold plate is actually the silver was, for the silver it was 300 something, 310, it was 310 nanometers. So the silver one should come in higher position, curve, like other one should come like this. This is the gold plate, this is the silver plate. Gold one is 248 nanometers, this is 310 nanometers, and this is 0 and this is EK max, and this is the lambda. No, that's how we draw the graph, kind of curve, right? So third part done. Fourth one, same photon beam of wavelength of 200 nanometers is incident to both plates separately. The corresponding photoelectrons measured from the silver and the gold plates are from the silver wavelength is 200 nanometers. Photocurrents measured, current produced by the photoelectrons is called the photocurrents. So from the silver plate photocurrent is Is, and from the gold plate photocurrent is Ig. These are photocurrents. State whether Ig equals to ISO, Ig is greater than ISO, Ig less than Is. Give reasons for your answer. Assume each photon incident on the plates ejects one photoelectron. So because we know that lambda for silver, lambda silver is 310 nanometers, lambda gold is 248 nanometers. So if we want to increase the photoelectric current, to increase the photoelectric current, the concept behind, to increase the photoelectric current, intensity should be increased. Intensity of the radiation should also increase. If we want to decrease the photoelectric current, we should decrease that intensity. We can change the energy of the radiation by changing the wavelength. Therefore, photoelectric currents are equal for 100 nanometers and 200 nanometer radiations. Therefore, Ig equals Is. We can finalize. Because we can change the energy of the radiation by changing their wavelengths. Therefore, the photoelectric currents are equal for both 100 nanometers and 200 nanometers. That part is also concluded. Next is, it has been reported that radiations of 222 nanometers can be used for inactivation of COVID-19 viruses, and however there is a limit, maximum limit of 24 millijoule centimeter per minus square per 8-hour exposure time for a human body when 222 nanometer radiation is used in medical applications. And what should be the maximum power of a point source which emits 222 nanometer radiations placed 20 centimeter from a person's COVID-19 virus contained palm? Take pi equals 3. So energy released from radiations without any harm during 8 hours is as of in the question, the energy released during that 8 hours is actually 24 millijoule Ca minus 2, right? So this can be written as 24 into 10 to the minus 3 joule Ca minus 2. And then also to remove the centimeters, we can write this as 24 into 10 to the power minus 3, 10 to the power 10 to the power 4. not just centimeter square, no, centimeter cm minus 2, so that's 4 jm minus 2. So that would be 24 into 10 jm minus 2. So for 1 second, energy released in the form of radiation without any harm for 1 second will be 24 into 10 divided by 8 hours into 16 to 60 minutes into 60 seconds, and that would be, yeah, just leave alone like that. And then take the release energy per second by radiation power and think that there is assumed sphere of radius 20 centimeters. So radius of 20 centimeters. It's easily not detectable, okay, of radiation placed 20 centimeter from the person's COVID-19. So radius is 20 centimeters, and we ask about the power equals P equals A divided by, actually it's the area, actually now we come to the area part, that is sphere is actually 4 pi r square. 4 into 5 is given as 3 here. 5 is 3, and radius is 20 into 10 to the power minus 2 squared, and that overall gives us 48 into 10 to the power minus 2 m squared. So energy going through the unit surface area of the sphere per second, energy per second passing through the sphere is power divided by that area. This is the relationship I wanted to get before. And then what they are asking is this, the power. What they need is the power actually. So we need to subject the power. P equals EA. So the power actually is 24 into 10, 8 into 3600, what we got beforehand at very first. So this equals to energy so this power equals to the power, maximum power is what we asked, maximum power divided by that area, that is 48 into 10 to the power minus 2. Then this P max is 24 into 48 into 10 to the power minus 1 divided by 8 into 3600, and then P max equals 4 into 10 to the power minus 3 joules per second, and this actually is 4 into 10 to the power minus 3 W watts. So this is how we get the maximum power in this case, as this power is already given, okay. So this is the part we had to apply here. So this is not something we expected, that's incorrect. So this P max is we need to find out for that area. This area is 20 centimeters. So that's pretty much all with this with regard to this question. So final part was a bit complex, and as it was a bit unclear as well because of these watermarks in this paper. So somehow we understood the concepts behind this, and for each of these steps carries a single mark. And please remember to revise the question again and answer these again and again until you make no mistakes. So thank you for watching this video. Have a nice day. Good luck.